Now let us lay the framework for the study of thermodynamics by beginning our second topic. Basic ideas and definitions. See, thermodynamics is a science. I will shorten it to thermo now, because thermodynamics is, in my opinion, too long a word. Mechanics, statics, even physics are much shorter words. But thermodynamics doesn't remain in an isolated box. It's a proper part of science, maybe a very proper part of physics. So it works with other branches of science, physics, chemistry, solid mechanics, whatever you have. You can't develop thermodynamics in isolation with other branches of science and other branches of physics. You can't study thermodynamics unless you study something in mechanics, something in fluid mechanics, at least the basic stuff. Something in geometry, which is also, in my opinion, a part of physics, on the borderline of mathematics and physics. So although thermodynamics defines its own ideas, thermodynamics inherits ideas from other branches of science, particularly other branches of physics. So any entity in thermodynamics, a property, a definition, an idea, a concept, will be called a primitive in thermodynamics. Primitives are those ideas, concepts, properties which are inherited or obtained from other branches of science, physics, chemistry, mathematics. So these are, thermodynamics says, well, these ideas are defined in, say, geometry or mechanics or physics or electricity and magnetism. We know what they are, let the other branches of science define them, explain us their characteristics. We will simply use them in thermodynamics as required. So the idea is like volume, pressure, velocity, etc. These are all primitives in thermodynamics. We will not define a volume in thermodynamics. We will not define pressure in thermodynamics. In physics, pressure is defined as force per unit area. We will say that, look, physics says pressure is force per unit area. We will use it like that. It's a primitive for us. No contest. It is defined well by some other branch of science and we will use it. There are some ideas which are not really primitive but are on the borderline of primitive. For example, the ideas of work and the idea of energy. These are defined in other branches of physics. For example, work done when a force is applied against a spring and the spring gets compressed, very properly defined in mechanics. Okay. So the idea of work is a primitive, but thermodynamics will formalize this. Similarly, the idea of energy is also defined in branches of physics. For example, you have a mass, and with respect to certain datum, it is at a height in a gravitational field. So, mass at a height has a potential energy that is defined in mechanics. We inherit that and consider that to be a primitive in thermodynamics. There are other components of energy, for example, kinetic energy of a particle or a body moving with some velocity v, or an extended body rotating along some axis. This has a kinetic energy of translation or rotation associated with it. A fluid flowing has a kinetic energy associated with it. That is primitive, but will also be formalized in thermodynamics. Work is a primitive which will be formalized by thermodynamics. Energy is a primitive which will be, let me say, will be redefined by thermodynamics. But it is necessary for us to be very clear about what are the primitives in thermodynamics, because we are not going to spend time on primitives. We will say this is a primitive, that means it is defined by some other branch of science, typically physics, and is used in thermodynamics. Then the second things are premises. Premises is a formal names for basic assumptions or the big heavy word laws. For example, you take geometry. All of us know about what is meant by Euclidean geometry, right? Now the Euclidean geometry is based on 5 postulates of Euclid: characteristic of a point, characteristic of a straight line, parallelism, etc., etc. Right? Characteristic of a point, there is no proof. These are basic assumptions on which geometry, Euclidean geometry is based. Similarly, the idea of mass, the characteristics of mass, is a basic assumption in mechanics. And particularly the laws of Newton. In classical mechanics, there is no proof for the laws of Newton. They are basic assumptions of classical mechanics. The whole of classical mechanics is based on that. So these are premises which are basic laws. For us, there would be a number of premises. Our premises in thermodynamics there are many. 3 of them are famous as the laws: zeroth, first and second, in some order. But there are other premises in thermodynamics which for some reason have not yet been given the state or the status of laws, but we will look at them as we proceed. For example, one premise is any isolated system tends towards equilibrium. This is a premise in thermodynamics. We say that if you wait long enough and don't disturb a system, keeping it isolated, we will find that it will reach a state of equilibrium. This is a premise. We have not yet defined what is a system, what is isolated, what is equilibrium formally, but since all of you have a background in thermodynamics, you at least partly understand what I am talking about. There are certain other premises which are known as state postulates. This is one of them. Another one which we will come to is a premise which is we are not conscious about, but which says that the state of a thermodynamic systems can be defined using only primitive properties. Okay. This also is a state postulate. It is a postulate, it is an assumption, it is a premise. For some reason it has not been given the status of a law of thermodynamics, but unless we make that assumption we cannot proceed significantly in our study of thermodynamics. A significant part of our study of thermodynamics will be the study of the premises of thermodynamics. Once that is done, what remains are derivations. Derivations are things which can be logically and using standard mathematical tools and some definitions derived from premises using appropriate set of primitives. For example, the idea of energy as a state function is a derivation. Similarly, the definition of entropy and its derivation is and its characteristic is a derivation. Similarly, the open system form of first law of thermodynamics. What we call the steady flow or steady state energy equation is a derivation. Then the formulae you have for availability, exergy, etc., etc. These are all derivations. Okay. Property relations, Clausius-Clapeyron relations, these are all derivations. So that is one part of thermodynamics, but the real understanding comes in appreciating the premises and undertaking the basic derivations as required for thermodynamics. Now we come to definitions in thermodynamics. See, they say that a picture or a sketch is worth 1,000 words. But if we start using pictorial language, I think people will get very confused. So we have to use words and we have to give very specific meanings to those words. We have to define things like a system, we have to define a thing like a property, we have to define a concept called interaction. For all these we have to provide a definition, and we will be using definitions of essentially two kinds. Definition we say is an explanation of something, so that something can be very compactly said in a word or two. So if you ask to define a human being, definition of a human being will require something like 30, 40, 50, maybe more words depending on the detail you want to provide in the definition. But once that is understood, everybody understands and we can make out whether I am a human or not, whether this pen is a human or not. Okay. So we will be having definitions of essentially two kinds. One is a definition which is a short form. For example, we will come sooner or later to this definition. We will say a process, a thermodynamic process, will be defined as, I have this habit of writing 3 lines indicating that what I am writing is a definition, is nothing but a change of state. That means that in any sentence, in any discussion, wherever I see a word process, I can replace it by the expanded form change of state, and the meaning should not change and will not change. Similarly, wherever I see change of state, if I have defined that as a process, well, I can replace change of state by a process. These are absolutely equivalent, just the way 2 is equivalent to 1 plus 1 in mathematics. So, you can say 2 is defined as 1 plus 1. So, wherever in mathematics you see 2, you can replace it by 1 plus 1, or wherever you see 1 plus 1, you can replace it by 2. So, these are just short forms. The second one, and perhaps the more important one, is a operational definition. Now, an operational definition, as the word goes, defines something, a property, a characteristic, a procedure, whatever, by defining a set of operations to either take a decision or to make a measurement and quantify. For example, black. I say the color of this pen is black. What is the operational definition? I say that in any form of light, if I look at it, I find nothing reflected from it, and hence I call it black. It absorbs almost everything which comes onto it is black. So, those who have studied heat transfer would have seen the definition of a black surface or a black body. It is defined as a body which absorbs any radiation of any form, any intensity, any direction, any wavelength which is incident on it. So, the operational definition is this: bombard that body or that surface by radiation of various kinds, various intensities, various wavelengths, various sources. If it absorbs each and every one of it, then it is a black. Otherwise, it is not black. That is one type of operational definition. Another type of operational definition is to specify a set of operations which will do a measurement and quantify something. For example, mass. How do you define mass? An operational definition of a mass would be: take a pan balance, a 2-pan balance, and a standard set of masses. Mass of a body is to be measured, put it in pan A, put the appropriate subset of the standard masses on the other pan, so that the balance balances. The value of the masses in pan B is the mass of the substance in pan A. That is the operational definition. Operational definition of a length would be: take a standard measuring scale. If I want to measure the length of this table or width of this table, align 0 to one edge, find out the mark at which the other edge is aligned to. That would be the operational definition. Operational definition has to be specified using things which are already defined or which are primitives in thermodynamics. And in particular, we want to see to it that we will not have any circular definitions. I write this and underline it maybe twice particularly because I have found during my study of thermodynamics and during my teaching of thermodynamics and continue to find even now that those who do very well in thermodynamics, those who are excellent thermal engineers, tend to understand some concepts of thermodynamics in terms of circular definitions. They tend to define heat in terms of temperature and temperature in terms of heat. And one assignment for you today, which you do not have to submit, is just go back to your study of thermodynamics and see whether you can define or we can understand the idea of heat transfer without any reference to temperature. If you can do that, then you can define temperature in terms of heat, no problem. Because you have defined heat first without a reference to temperature. So, while defining temperature, you can refer to heat. Or can you define temperature without any reference to heat transfer? If you can do that, then you can define heat in terms of temperature. But quite often you will find that many people, those who have become successful thermal engineers also, and many textbooks in thermodynamics and some very good textbooks also fall in this trap. They tend to define temperature in terms of heat and heat in terms of temperature. That is a circular definition. And a typical circular definition is something like this. You ask, what is x? And you will say x is y plus 3 by 2. Fair enough. Then you say, okay, now explain what is y. And you will say y is 2x minus 3. What have you done? You have defined x in terms of y and you have defined y in terms of x. You know a relation between x and y, but you can't get either the value of y or a value of x. There is a book by Noth, I like to refer to that, in the index of which, it is on computer programming, in the index of which if you try to see circular definition in C, it will say C definition circular. Fair enough. Then you go to D in the index, and in definition among various types you have a circular definition, and for circular definition circular, he says C circular definition. So all that you go is go in a circle. That is exactly the meaning of a circular definition. It makes you appreciate what circular definition is without telling you exactly what circular definition is. We do not want to get into any such trap, and hence we are going to essentially look at, operational definitions. Now let us start our study of thermodynamics by defining our first definition. And that is we will now define a thermodynamic system. We are going to have an operational definition. So we are going to say that how do we decide whether a given entity is a thermodynamic system or not. If you look up the books, you will find thermodynamics entity is a region of space in which we are interested. It may contain mass, it may contain energy, it may contain both. It will have some boundaries, some real, maybe some imaginary, some flexible, some inflexible, all sorts of things. For us, a thermodynamic system will simply be a region of space of our interest. This is important because a thermodynamic system is never dictated to us by nature. It is we who define a thermodynamic system. So it is a region of space of our interest, the way we define it, and of which the boundaries are fully defined. By fully defined, we mean that it must be a completely enclosed space, that is all. And fully defined means that at any instant of time, we know what the location of the boundary is. So that means any properly bounded zone of space, whatever be its content, maybe from pure vacuum to very densely packed stuff, is a candidate for a thermodynamic system. Only when the boundaries are defined, a system is defined. If the boundaries are not defined, the definition of a system is not complete. So the importance of a system is that its boundaries must be well defined, and that automatically means that it is a region of space. Sometimes we say that it is absolutely necessary for us to know what is inside a system, but from a thermodynamic point of view, it is not necessary for us to really know what is inside the system. If we know something about it, it's okay, but if we know nothing about it, also that is okay. From a basic or pure thermodynamic point of view, we don't have to know what is inside a system. So is this an operational definition? I think it fits the candidature of an operational definition because we can define whether a given entity is thermodynamic system or not. All we have to see is whether the boundaries are properly defined. If it is so, then it is a thermodynamic system. If it is not, well, it is not a thermodynamic system. Now, a question almost always comes up is the sun a thermodynamic system? The answer is yes. If we can define the boundaries of the sun and say that it is a, say, a sphere or an ellipsoid with this center and these coordinates, this radius or these axes, then well, it is a thermodynamic system. Then the question is the solar system a thermodynamic system or not? Then don't just say the solar system, define that region of space in the Milky Way galaxy which you call the solar system, define its boundaries, and you have a system. It is important to know that the boundaries may be physical, as the boundary of this surface of paper, or if you have a glass of water, the inside of the glass of water, it is a boundary. Or it could be an imaginary not in a mathematical sense, it could be purely defined at some surface which you can imagine with some coordinates, but which is not a physical surface. It could be physical, it could be defined. The boundaries could be flexible, they could change shape and size. It is also possible that the boundaries may be continuous, like a single drop of water, or the boundaries could in some cases even be discontinuous. You take the drop of water and maybe make it into two small drops of water. You have two disjoint boundaries, but it is possible to consider that as a single thermodynamic system. Continuing with our discussion on the boundaries, which came out of the idea of what a thermodynamic system is. And I think you have already appreciated the importance of boundaries, because unless a boundary is there and it completely encloses a thermodynamic system or completely encloses a region, we can't call that region a thermodynamic system. Now, what type of boundaries can these be? I have already listed here, some boundaries are physical, some boundaries can be defined, some boundaries can be flexible, some boundaries can be inflexible, solid. Let me take some illustrations. Being mechanical engineers, we are used to engines. We know our IC engine and refrigeration compressors are cylinder piston arrangements. The old steam engine, many of our reciprocating pumps are cylinder piston arrangement. So you typically have a cylinder, generally closed, and a system. Now let us say that the innards of the cylinder, the inner surface of its head, the cylindrical part, and the top surface of the piston. These are boundaries which enclose a region of space, and so this is our system. It may contain a liquid, a gas, or whatever. Then during some interaction, the piston may move up and down. What happens to the boundaries? First, all the boundaries are physical boundaries. You can see them, you can touch them, can characterize them. Okay? Real surfaces, real physical surfaces. You can disassemble it, feel the top of the piston, feel the inside of the cylinder head and the surfaces. As the piston moves up and down, the cylinder head boundary remains fixed, no change in it. The top part of the piston boundary, this boundary moves up and down, different locations at different times. The side boundaries, sometimes they are short. If the piston goes down here, the piston head boundary moves here, the side boundaries extend. So these are extensible boundaries. These are illustrations of physical boundaries, some fixed, some moving, some extensible. Sometimes we will take a system, you take a section of a pipe through which some fluid is flowing. And we say that, look, we are interested in what happens to the fluid as it moves between this plane and this plane. And we can define the system as the following boundaries. The inner surface of the tube from plane A to plane B, and the surface of plane A as it cuts through the tube, the surface of plane B as it cuts to the tube. The boundaries A and B can be sketched on a drawing, but you can't feel them. We have put them there as dotted lines. So these are illustration. The inner surface of a tube is a physical boundary. This as well as this, these are imaginary or defined boundaries. During a process, I may move this boundary B further in and out, but at any time I must know where my boundary B is. Similarly, A I can move in and out, but at any time I must know where that boundary is. The tube may be flexible. This may be a physical boundary, but it's a rubber tube. I can pump in high pressure water and it can expand. It could be flexible. The arteries and veins in our body are illustrations of such flexible boundaries. And I can say plane A is the exit of my heart and plane B is the inlet to my lungs or something like that. So this is an illustration of an imaginary boundary. Another illustration of a system consisting of purely imaginary boundary is this. In fluid mechanics, we derive the so-called continuity equation, a differential equation representing the conservation of mass. In heat transfer, we derive the differential equation of conduction, a differential equation representing a combination of Fourier's law of heat conduction and the conservation of energy, or the first law of thermodynamics. To do this, we say, imagine a control volume of size delta x by delta y by delta z. Take any good book on on fluid mechanics or heat transfer, or even on solid mechanics, where differential equations of equilibrium are, and we say let this be delta x, let this be delta y, let the third dimension be delta z, somewhere in our domain of interest. Now we are defining 6 surfaces enclosing a small system. This is a thermodynamic system, but it has all boundaries are defined. None of them is a physical boundary. You say let at some point let this be some point x, y, z. So you can locate all the 6 surfaces and you determine how much mass comes in from which surface, how much mass goes out from which surface, and write a mass balance and derive a differential equation. This is an illustration of a system containing, made up of purely imaginary or defined boundaries. But at any time we know what is the location of each and every boundary. But I cannot touch the boundary. I can't touch my finger to it. If I try to put a finger will go through because there is no real boundary associated with it. Now boundaries are important not only from the point of view of defining a system, they are also important from the point of view of what happens to the system. If you change the boundaries of a system, you are creating a different system. Take for example a simple brake. You have a drum, I am showing only a part of a drum which is rotating, and there is a brake shoe which is being pressed against it. And I want to study the interaction between the shoe and the drum. There is a boundary between the shoe and the drum, and I can define my system, say of the shoe, with a boundary just inside the shoe and the other boundary of the physical extent of the shoe. This is one system. Then I can have a system in which the boundary is exactly the interface of the shoe and the drum, and the third boundary which is slightly inside the drum. So these three boundaries define three different systems. And later on maybe we will come back to this as an exercise or a homework. The interaction between the drum and the shoe will be discussed, and you will realize that as you change the location of the boundary, maybe just by a few millimeters, in one case inside the drum, in another case inside the shoe, you will find that an interaction which you are confident to be work interaction turns out to be purely a heat interaction, just because you have changed the boundary. But remember, there is no contradiction here. You have changed the boundary, so you have changed the system, so you have changed everything. So if an interaction of the work type now turns out to be an interaction of the heat type, there should be no surprises in it. Okay. We will come to this later. This was just an illustration of something which is going to come up later. Now let's stop the thing here. We have defined what is meant by a system. System has to be enclosed in boundaries of some type or the other, physical or purely defined, fixed or flexible or extensible, etc. Enclosed in boundaries. We know what the importance of boundaries are. So a system and its boundaries are one and the same. Boundaries define a system, system is defined by its boundary. So enclosed space defined by boundaries. The next thing is what typically we talk about
is classification of systems.
Now in thermodynamics, we will never talk about just one system. In thermodynamics, we will always talk about a system A and a system B, almost always. And we will say system A and B, they interact with each other. There is some sort of a transaction. They talk to each other, they play with each other, there is a give and take. We will define an interaction later. But there is some sort of an interaction, a transaction you may call it. Something is given, something is taken. Okay. Many textbooks define a system and the surroundings. Surroundings are defined as something which is outside the system. But let us not be so vague. For us, the surroundings is also a system. So its boundaries also have to be defined properly. So, the surroundings is as much a system in its own right as is our main system. Actually, it would be better to talk about a system A which is interacting with system B, because remember that if we say that surrounding is whatever is outside the system and leave it without defining its boundaries, then we are going to get into trouble, because then we have not defined the surroundings as a proper thermodynamic systems. And whatever we define for our system and the laws of thermodynamics are applicable only to systems which are properly defined. They are not applicable to systems which are not properly defined thermodynamic system. So, although we may be using the word surroundings, we will define it as a system B which is next to system A and is interacting with it. Okay. So, keep that in mind, because many textbooks will keep the definition of surroundings vague. We will not leave it as vague. We will say that the surroundings is a system in its own right, very properly defined, and hence all its boundaries will also have to be defined. We may call this as the primary system, which is of primary interest to us. This is a secondary system in which we are not that much interested. Maybe we do not want that much detailed study of the system, but it is a system in its own right, although we may call it a surrounding. Okay. Now, in the classification is usually, say we have a closed system, or we have an open system, or we have an isolated system. I have a problem here, because a system by itself with its boundary defined cannot be closed, open or isolated. This classification should come slightly later, because this classification pertains to systems undergoing a process. We have not yet defined the process, but a system is just there by itself, not interacting with any other system. Then there is no question of its being closed or open or isolated. A system by itself is something which is enclosed in boundaries. We do not ask what is happening to it. Only when we talk of a process, we talk about what is happening to it. Okay. So, actually we should push this definition after a study of processes, but most textbooks will talk about this classification just after the definition of system. So, let us get it over with. All this thing has to do with interactions. Again, we have not defined a process, so we have not talked about interaction. But let us get over it. We have said the science of thermodynamics talks about energy and energy transfer between systems. Okay. So, unless there is an energy transfer, thermodynamics does not take much interest in that. So, what we will do is we will say that we will put 3 columns or 2 columns: energy transfer, mass flow, and name. If we say energy transfer is allowed, that means system A can do either work or transfer heat to system B. Again, work heat we have to define. We are just overtaking that just to complete this definition. But no mass flow is allowed across the boundaries of the system. Then the name given to that system is a closed system. Okay. If energy transfer is allowed, mass transfer also does take place, then we call the system an open system. If, on the other hand, no energy transfer is allowed and no mass transfer also takes place, then we call that system an isolated system. This is the classification. Now there are some names, slightly different names, which are also used. For example, the closed system. There is no mass flow across the system boundary, so the mass of the system remains fixed. So quite often a closed system is also known as a control mass, indicating that the mass is controlled or mass is constricted to remain within the system. Unfortunately, for some reason, the open system has a very common name called control volume. This is unfortunate because the control volume and the short form CV is so common that quite often in textbooks the subscript CV is used to represent an open system. The unfortunate thing is, in a control mass, a closed system, mass is fixed. It does not change because there is no mass flow across the boundaries. But in an open system, the volume need not remain fixed. The volume can go down, can decrease, increase. So the volume is no way fixed. It may be controlled in some way, but it is no way fixed. So don't be under the idea and don't let your students absorb the definition of an open system as a control volume, where they appreciate control volume as a fixed volume. It is not a fixed volume. And for that, we again take the illustration of our common illustration of a cylinder piston arrangement. Again, I will show a cylinder and a piston. And let me say it is part of a pump or an engine or a compressor which has two valves. Valve 1, valve 2, piston P. And let us say that again our system is whatever is within this domain. I say that both the valves are closed. What is the type of the system? Our system will be a closed system. Now, if say one valve is open, then do you say it is an open system? The answer is open system only if fluid is flowing in or out of that valve. Otherwise, just because a valve is open does not automatically make it an open system. Take this illustration. I am thirsty, so I see this water bottle. Show me. So I am thirsty, I see this water bottle. Now I am teaching thermodynamics, so I look at it and say, is this a system? And I say, yes. I may define the system as the inner surface of the bottle, including the inner surface of the cap. So it may contain the inside partly water, partly air. Or I may define the system as water itself. So what is the system? The surface of the water, that is wherever it is in touch with the inside of the bottle, that surface plus that top surface of the water. I am neglecting the evaporation of water. So if I move it, the top surface and even the side surfaces are either extensible, flexible, they can be as complex as they like. But if I neglect evaporation, it is a closed system. Again, let me say that my system is water and air above it. I open the cap. Just opening the cap does not make it an open system. But if I blow air through it, or during the process of drinking water, something has come out of my system. So I have allowed a mass flow rate. I have noticed that there was a mass outflow from this system A, I was system B, there was a mass transfer of mass, transport of mass. So during that transaction, it was an open system. And just now if I keep it here and neglect that small air movement, then it will back to be a closed system. The thing to remember here, its system by itself cannot be open or closed. We have to look at the process, which we will soon come to, and then decide whether it is an open system or a closed system. So remember this, that only when you look at the process of a system can we assert that a system is open or closed or isolated. Now, how do we describe a system? We describe a system, we do this in a thermodynamic fashion. So, how do we define a system thermodynamically? See, we are interested in the following. We are interested in the change of a system. In what way has it changed? That bottle which was my system earlier had lots of water, now it has lesser amount of water. So there is some change in the system. Maybe initially the water is cold, I hold it tight in my hand, warming it up. Maybe the temperature had changed. We have not defined temperature, so don't be in a rush to assume that I have defined temperature. We will do it much later in the course. So something has changed in the system. So we describe the system by defining the state of a system. So that means we have to define what is meant by the state of a system. Okay. And now we come to the second important definition, the state of a system. And the state of a system will bring it to the third important definition, the property of a system. The state of a system, the operational definition of the state of a system is this. The state of a system is defined when we do the following. Two-step process. List all relevant characteristics of the system. And I will jump the gun slightly. Each relevant characteristic we will shorten this to one word property. Each relevant characteristic is each property. So, let us take an illustration. Okay. And let us say that the inner surface of this is our system. It contains a gas, and we are going to do some funny things with the gas. So, we want to know what happens to the gas. So, we will list relevant characteristics, that is properties. Now, maybe we will say volume, is a relevant characteristic, maybe mass is a relevant characteristic, pressure may be a relevant characteristic. We have not defined, but we know something about temperature, a relevant characteristic. Okay. Now, the shape of the cylinder, whether it is spherical or whether it is cylindrical, is it a relevant characteristic? We do not know. It all depends on what we are going to do with it. Okay. The cylinder may be lined inside with maybe rubber or maybe glass, or it may be painted inside with some anti-corrosive paint. The type of paint, the type of lining, is it going to be a relevant characteristic? We do not know. It depends on what we are going to do with the gas. So, all that we appreciate is, if we start looking at the detail, we can come up with a long list of relevant characteristics, a large list of characteristics. Not all of them may be relevant. Relevant characteristics will be only those which are of use to us, in which we expect to see any difference or change during our play or process of the system. So, how to decide on the relevance? Thermodynamics does not tell us anything about it. It is only out of experience that we decide. For example, we know from our experience that generally volume, mass, pressure and temperature, these are the four relevant characteristics. The shape of the cylinder or thickness of the cylinder, type of inner lining, whether like the bottle which I showed you, whether the shape is serrated or plain, maybe that is not a relevant characteristic. So, the first thing is this. First item in definition is list of properties. The second step is to quantify the properties. That means we must do an experiment or we must do some measurement to provide numerical values to each of these properties. Maybe we can use some geometric tricks to measure the volume. Maybe we can use a weighing machine or a mass balance to measure the mass. We can fix up at the top of the bottle or the cylinder a pressure gauge to measure the pressure. We can insert a thermometer to measure the temperature. And maybe we will come up with results like volume is 1.2 meter cube, mass is 20 kg, pressure is 6.9 bar, temperature is 32 degrees C. So, what we have here? We have a list of relevant characteristics, that is properties, and its quantification. That means to each of these properties we have assigned a numerical value. That means we have quantified, a quantity is associated with it. And be sure each quantity will have a numerical value and a unit of measurement associated with it. When it comes to solving problems, we will again emphasize this, the various units and their significance. So, when we do this, we say that now we have defined state of our system. And while doing this, our third thing, so our definition 1 was system, and along with that we understood the importance of boundaries. The second definition and third definition more or less went together. State of a system, and property or properties of a system. The property of a system again emphasize is a relevant characteristic. Singular. Okay. Now, let us discuss something more about the properties. Just now we have seen, and for simple gaseous things we have listed out volume, mass, pressure, temperature as properties. Later on we will come across energy E, enthalpy H, entropy S, maybe kinetic energy, thermal energy. These are all typical properties that we come across in thermodynamics. So, let us look at the classification of properties. You will notice that some of these properties, volume, mass, pressure, are defined in other branches of physics. So, that means these are primitives. So, one way of classification is primitive properties. These are defined in other branches of physics, and they are just inherited by thermodynamics. Physics or chemistry or geometry, whatever. So, volume comes out of geometry, mass comes out of mechanics, pressure comes out of mechanics, fluid mechanics, whatever. And later on velocity, kinetic energy, potential energy, electrical energy, all these things are primitive properties. Property can be primitive, a property can be basic thermodynamic. A basic thermodynamic property is a property which is defined using the laws of thermodynamics. we will soon see that the three laws of thermodynamics which we are going to study, zeroth, first and second, each one of these laws will help us or will force on us a basic thermodynamic property. Zeroth law will define temperature, first law will define energy, second law will define entropy. And these three and only these three are basic thermodynamic properties. Right? Out of which E has a special status because energy is defined not only in thermodynamics but in other branches of physics. So, the thermodynamic part of this, later to be known as the thermal energy, U, you can consider as a basic thermodynamic property. But the fact remains that there are just three basic thermodynamic properties, one for every law of thermodynamics. Zeroth law helps us with temperature, first law helps us with energy, second law helps us with entropy. And the third one is derived thermodynamic properties. These are properties which are combination of properties. And they are useful because these are useful short forms. Perhaps the most famous of this is enthalpy. We will find that the combination of property U plus PV comes up so often in thermodynamics, particularly when we look at fluid systems or open thermodynamic systems, that we find it useful to define one letter for it and call it enthalpy, H. Okay. Later on, you will even have, for example, the Gibbs function. This is also a derived thermodynamic property. There are properties which are derivatives. For example, Cp. Partial of H with respect to T at constant P. Similarly, Cv, partial of U with respect to T at constant V. The so-called specific heats, an unfortunate name, we will discuss that later, but these are derived thermodynamic properties. And such derived properties are common in other branch of physics. For example, stress, strain are properties, useful properties or useful characteristic in solid mechanics. Okay. Their ratio, the Young's modulus, is a derived property.